Hello friends, I'm Nikita and you are watching Prepare for GATE. GATE is a competitive objective examination. It has 65 questions of 100 marks. The duration for this exam is 3 hours. So not much time is given for you to solve 65 questions. Moving with our lecture series on communication, let's discuss today's topic that we are going to discuss. Firstly, amplitude modulation and demodulation, the spectra of AM, a demodulator known as Superheterodyne receiver. So, the topic to be discussed will be, as in reference with the syllabus, is amplitude modulation, demodulation, spectra of AM, figure of merit of amplitude modulation, and superheterodyne receivers. What is amplitude modulation? Now, in communication, there are three types of variation that helps in modulation. That means modulating a signal so that it can carry an information. In communication, a signal x of t is equals to a of t cos omega t plus theta t, where t is the time reference. The signal can be modulated in respect to its amplitude, frequency, and phase. Such modulations are termed as amplitude modulation, frequency modulation, and phase modulation, accordingly whichever is being modulated. Such signals are termed as amplitude modulated signals if their amplitude is being modulated with the message signal. Now consider a message signal xt is equals to am cos omega mt and carrier signal xct is equals to ac cos omega ct. Okay, these are the two signals that will be the basics of our modulation process. X of t will be the message containing the information and it will be a low frequency message, and xct will be a carrier signal which will have quite a large frequency. So amplitude modulation are further divided in 5 different communication: double sideband, double sideband suppressed carrier, single sideband suppressed carrier, and vestigial sideband. Moving further, we'll discuss what is actually baseband and carrier wave communication. Message signal is a baseband signal, and when it is modulated on the carrier frequency, it is termed as a carrier wave communication. Often the messaging signal like voice, audio, and video are usually low frequency signal concentrated near to zero of the spectrum. Spectrum is like a coordinate system, just like we have x and y graph. It is in coordinate systems, and similarly in frequency domain, the x line is represented by a frequency line f line, and the y line is the amplitude line. So that's the spectrum. Thus, these signals are termed as baseband signal. So those signals which are concentrated near to the zero of the spectrum, which have low frequency content, are known as baseband signal. Such signals can be transmitted only through coaxial cable or copper wires. Earlier, thousands of kilometers of cable were spread out from door to door, making connectivity possible for low frequency signal to propagate, and can be heard on either side through telephone as the end device. However, with advancement in technology, voice propagation through mobile phones become prevalent. Here the media to travel was space, air. The low frequency signal traveling through space get absorbed in between and fails to reach receiver. Such limitation of baseband communication give rise to linear carrier wave communication. But I hope you have got why there is a need for communication or why there is a need for modulation. Baseband signals lacks the energy to be transmitted through the air, so they are modulated on high frequencies so that they can be transmitted easily through air without getting disturbed by the channel disturbances and get received at the receiver. Now look at what is a modulated signal and what is a carrier signal. No, actually in this figure I have just shown you only the basics. These graphs have been drawn with the help of a grapher, and you can see that the time period for both these graphs is different totally. For a low frequency having 2 Hz frequency of a message signal, a much clearer graph is formed having a considerable time period. A carrier frequency having large frequency content such as 100 Hz have a small time period. They are very congested in the time domain. Now you can see the modulated signal over here. The modulated signal so formed will superimpose the message signal over the carrier signal. Now you can see this is a AM double sideband AM signal 1 plus 0.1 0.7, and it is an under modulation signal. How I am saying all these parameters just by looking at the graph, you will come to know when you move further through these video lectures. So this is probably it. The high frequency signal, carrier wave signal, taking the message signal along with them. Now let me talk about some of the parameters that can be calculated. First of all, power, modulation index, and modulation efficiency. These 3 parameters are calculated for amplitude modulation and considered to be very important. Now, power of a modulated signal can be calculated using carrier power and sideband power. If you see, the spectrum will be like in frequency. If we are talking about a frequency domain, it will be like a power at here, a sideband power at here, a sideband signal at here, and another sideband signal at here. This will be the spectrum of a double sideband having an amplitude AC at the center and AC mu by 2 at the sidebands. Now modulation index mu of a modulated signal is equals to amplitude of message signal divided by the amplitude of the carrier signal. Amplitude of message signal is AM and amplitude of carrier signal is AC. Now, if you wish to have an overmodulation, then mu should be greater than 1. For 100% modulation, mu should be 1, and for an undermodulation, mu is less than 1. If mu is equals to 0, then no modulation have occurred. That is, no superimposition of message signal on carrier signal have taken place. Efficiency of modulated signal is power of sideband divided total power, which is given by this formula. Now look at this gate question. Pause for a minute. Don't go on the solution right away, though I have given you. Let's start with explaining the question to you. You can also try it by yourself. This is a very simple question. The unmodulated carrier power is an AM transmitter is 5 kilowatt. The carrier is modulated by a sinusoidal modulating signal. The maximum percentage of modulation is 50%. That means mu1 is 50%. If it is reduced to 40%, then the maximum unmodulated carrier power in kilowatt that can be used without overloading the transmitter. Overloading the transmitter here means that it should not exceed the total power. So I have mentioned like mu1 is this, mu2 is this, and power of carrier is AC square by 2. Total power of a double sideband is given. AC square by 2, 1 plus mu square by 2. Or you can say PC is equals to 1 plus mu 1 square by 2. Now on solving, PT is 5.625 kilowatt. Keeping PT constant, the new PC at modulation of 40%, 0.4 will be 5.21 watt. Okay. So instead of 5 kilowatt, we'll be requiring 5.21 watt if we wish to send a signal on a modulation of 0.4%. Okay. Now moving forward, what is actually a double sideband? We have been talking about double sideband quite a lot now. So discussing about double sideband, I have already told you like what is a message signal, how it is represented, and what is a carrier signal. To get to know the expression for a double side signal band, if we expand our basic expression of modulation, then it will comes out to be AC plus AM cos omega MT cos omega CT, where AC is equals to 1 plus, if we take AC outside, 1 plus AM by AC cos omega MT omega CT, where XT is AC 1 plus mu cos omega MT cos omega CT. If you calculate it, you will get this result one. On Fourier transformation, you will get 0.5 AC delta function of del F plus FC plus del F minus FC plus 0.5 mu of AC x FM plus FC plus x FM minus. Now this is the Fourier transformation of the double sideband. You can see at FC frequency there is a arrowhead, and at FC plus FM and FC FM minus FC there is again two sidebands. Okay, to calculate the power of PC, we'll integrate our signal XCT, carrier signal, over dt, and from 0 to 2 pi AC square cos square omega dt we'll get AC square by 2. Here I'll suggest you to do the integration, though I have told you all the steps, but still I think in practice of integration will help you to be better at gate, because you need to solve questions within a time frame of 2 to 3 minutes. Such practicing will increase your speed. Okay, so keep on practicing about integration differentiations so that you'll be able to have a speedy calculation for gate examination preparation. So power of sideband is mu square PC by 2. Okay, and if you further divide the sideband power into an lower sideband and upper sideband, it will be mu square PC by 4. So total power, as I have already shown you in the example can be derived by the steps taken above. And the efficiency is total sideband power upon total power. And again, that formula which I have told you earlier is derived by this basic formula. The bandwidth of the modulated signal will be 2 FM. Though it has been modulated to a high carrier frequency, still the bandwidth will remain the same. This is a representation of a double sideband. Now again, going with a second question on this is a GATE 2016 examination. Throughout my lecture series, you will see a considerable questions which I have taken exactly from the GATE question that will help you to prepare better, because keep on trying to solve more and more questions that will enhance your practice and help you in solving 65 questions of 1 marks or 2 marks. Okay. In 3 years in 3 hours of time span. So moving forward, if we see that ST is an AM signal, just like a modulated signal, having 3 frequencies content at 1800, 1600 and 2000. Its actual frequency, if we divide this frequency in 2 by F, then F will be equals to 1000 in this case, 900 in this case, and 800 in this case. So the 901 lies in the middle. You can go by a thumb rule that what lies in middle of the total spectrum is our signal at FC frequency. If you see that 900 is the FC frequency, then this is a sideband, this is another sideband. And from here we can observe that AC is 20 watt and AC mu by 2. The amplitude of the sideband is equals to 5 watt. Now substituting the value of AC, we'll get mu equals to 0.5. Now this is a very simple 2016 1 mark question. Now again, moving forward, the modulation on DSB. Now there are different techniques which are helpful in modulating AM signals. First, talking about the double sideband, a multiplier modulator is used, having an input mu of xt and output AC cos omega ct plus mu of xt into AC cos omega ct. If you take AC cos omega ct common, you will get 1 plus mu xt. That is our output. By a non-linear modulator, what happens in this, if you see, with the help of the adders and a non-linear modulator, we'll get our message signal. In non-linear modulation, we do b into x square t, squaring a signal, and when you square a signal and pass through a low pass filter, you will get 2am 2a mt plus 4b mt cos omega ct. Okay, that will become twice of the initial message signal, and it will be 4 times of the initial message signal with a multiplication of cos omega ct. Now there is switching modulator and a ring modulator. Not much have been asked. You can just go through the diagram and see how it functions and the basic calculations. Okay, now the balance modulator. Balance modulator is a simple modulator where you can see it consists of 2 modulator and an adder. In first modulator, you are getting and S1T AC 1 plus K KMT cos omega 2 pi FCT. Now this particular signal is for a suppressed carrier, DSB suppressed carrier. If you can see the power required to carry a carrier signal is not present in the whole expression. It has been dropped. So such kind of signals are termed as double sideband suppressed carrier. These signals are good in amplitude modulation because they require less power in consideration to the earlier signal. And they can be modulated using an amplitude modulator with empty signal minus empty and empty passed through a modulator with an oscillator with FC frequency and added. When these two are added with a minus sign, okay, we get a final suppressed carrier DSB signal. Moving with demodulation of DSB, we have Rectifier Detector. Rectifier Detector is a diode detector with a low pass filter and a CR circuit. You can see with the help of the diode, the waveform is chipped off. When it is chipped off and only a positive frequencies is present, then the variation in the signal amplitude contains the information. These variation in these signals when passed through a low pass filter retrieves the baseband signal of low frequency, and on passing it through CNR, it further deteriorates its amplitude and get you the actual message signal that was originally your message. Now, envelope detector follows the output of a modulated signal. Now, you can see a very good example in this, like if you see the amp with the help of the C and R filter, okay, with the help of the C and R like capacitor and resistor, the output follows the trail of the input signal. You can see with the CNR, it gets charged up to its peak value and then the capacitor discharges till it reaches its next peak value. And it again charges to that peak value and it again gets discharged. And it again, when it reaches the signal again, it reaches to its peak value and again get discharged. The whole step is being followed, keeping in mind that RC should not be too large so that it doesn't follow the path of the modulated signal. Now the figure of merit of DSB can be calculated. Like figure of merit, I have shown here the power spectral density. What is power spectral density is being already discussed by me in my previous lecture on random variables and process. So if you don't know the power spectral density, please go through that lecture and you'll come to know what exactly the power PSD of a signal is and how it is being calculated. Moving further, we have the PSD of a baseband noise signal, and which is N0 omega. The input signal we can be calculated by A square by 2. The input signal power over the noise power is A square upon 2 N0 omega, and similarly is the output power. So the figure of merit is 1, and which is not affected by any change in phase. To calculate a DSB-SC signal, moving further, we have calculated the DSB signal already, and now if you are calculating a DSB-SC signal, you can see it's AMAC by 2 cos omega C minus omega MT plus omega C plus omega mt, that is, it contains only the sidebands. Kindly look at the steps that has been explained over here very clearly, and in further, like in frequency domain, it will be represented by xfm plus fc plus xfm minus fc. So that will be the whole representation. Now, if you see over here that if our message signal is like this, and when it is modulated in frequency domain, it is almost like a Gaussian bell curve. When it is modulated on a high frequency signal, it has two sidebands. At the output, one of the sideband, this is the spectrum. This is a spectrum that I was talking to you about earlier, but what a spectrum was near the low frequency, right? The zero of the spectrum, if you can remember. I think you can. And this is the process how we demodulate. Now, demodulation of DSB-SC, as I have already discussed earlier, with the help of envelope detector or a rectifier. If you don't understand, if you couldn't recall it, then please go few minutes back and you'll definitely get it what were the two different demodulators that I have talked about. Moving further, how to demodulate a DSB-SC. The reconstruction of the original signal is done by multiplication of the incoming signal, followed by a low-pass filter. The synchronous detection or coherent detection is used to restructure the original baseband signal, which are in phase to the original signal. The local oscillator carrier at the receiver in frequency and phase coherent synchronism with the carrier used at the modulator. Now we have talked a lot about DSB and DSB signal. Let's further talk about single sideband. Now, if you can see in this graph, in this picture, this is a double sideband with a suppressed carrier. This is a message signal. Now, if you further suppress this signal message with only FC plus W frequency content, then also it will be carrying the full information, not the full information, but the sufficient information required to be carried. So, if we see the expression for representation of the modulated signal for SSB signal, single sideband signal, it is AC/AM by 2 cos 2 pi of FCT and cos 2 pi FMT minus plus AC/AM by 2 sin 2 pi FCT and sin 2 pi FMT with a bandwidth of W Hz. Now the modulation of the SSB signal is done to phase shift method and selective filter method. In phase shift method also, if you can see, an oscillator is there with the FC frequency, a phase shifter is there which is converting the carrier signal by a phase shift of 90 degree. Here the message signal is being converted by a phase shifter. Most probably you'll know them by a Hilbert transformation process in communication terminology, and that signal is being added. On adding, we'll get a SSB signal. Moving further, you can see how this Weaver's method is used to calculate the SSB signal. Here I have shown you all the 10 frequencies that you get at each step. Will really clearly, you will have no doubts about at each step what kind of frequency is being transmitted. So please go through this very carefully, okay, and remember it so that you won't have not a single doubt about how this frequency is being transmitted. Demodulation of SSB signal. A synchronous demodulator can be used to recover original signal from the SSB signal. A higher frequency signal present can be chipped off by passing the signal through a low-pass filter. Now talking about vestigial sideband. Vestigial sideband, instead of rejecting one sideband, which we have earlier seen in SSB case, there is a gradual cutoff of the other sideband. With the help of an envelope detector, you can demodulate the signal. Okay. Now moving further on the frequency division multiplexing. Now these questions often come in gate examination too. What happens in our real life that is being actually shown, done with FDM. Now channel is one, but on the same channel, multiple message signals are being transmitted with same carrier frequency or with different carrier frequencies. Okay. Now throughout the lecture slides, we have come across various AM signals, DSB, DSB-SC, SSB and VSB signals, and the parameters required to solve these. But now we are moving forward with the demodulation, and there is one specific demodulator that has often been asked in gate examination, that is superheterodyne receiver. Before that, let's see here what are the characteristic parameters of receiver. As we know, the AM signal lies between 550 kHz and 1650 kHz with a bandwidth of 10 kHz. An FM signal lies between 88 MHz to 108 MHz with a bandwidth of 200 kHz. There is a special terminology that is often considered for the selection of the receiver of AM modulation and FM modulation. It specifies the ability of receiver to allow only selected tune station and rejecting all possible undesired station. That is, it accurately selects only that frequency that is required and rejects all other frequencies. It depends on the characterization of tuned amplifier. What is meant by sensitivity is discussed with me over here. You can see that with a gain of 10, all the signals have the almost same amplitude. But with a gain of 100, you will see that it's get on 0.1 volt also. It is the possible strength of the receiver to be maintained to produce corresponding faithful output. The sensitivity of receiver mainly depends upon the collective gain of the amplifier, as there is a limit of getting gain, as only limited number of amplifier could be cascaded together, otherwise amplification would be affected by loading effect. Sensitivity of receiver mainly depends upon the collective gain of amplifier. Okay. And fidelity, it is the ability of receiver to produce all possible frequency component of the transmitted audio signal. Now these three parameters are considered in choosing the characteristics of receiver. Now functions of TRF. The performance of the receiver is increased by proper selection and rejections of frequencies. The RF amplifier, demodulator, AM amplifier and power amplifier are the amplifier which are present in the demodulator when the signal is observed and it's passed through all the stages and get on the end product. An RF amplifier, a tone amplifier, performs proper selection and rejection of a receiver. It is called a qualitative tuned amplifier, as it tunes only one frequency component having bandwidth 0 and quality factor infinity. Quality factor is dependent on two things, that is the frequency and the bandwidth. Thus, the bandwidth increases, the sharpness of the curve decreases. The bandwidth is equals to resonant frequency upon the quality factor. Also, the resonant frequency is Fr is equals to 1 upon 2 pi under root LC. To change tuning of TRF receiver to different possible station, correspondingly, the resonant frequency of tuned amplifier should be changed such that Fr is equals to Fs. Now, for proper selectivity of the receiver, the bandwidth offered by tuned amplifier should be 10 kHz for an AM signal. For tuned amplifier receiver, as Fr changes correspondingly, the bandwidth offered also gets changed, so the selectivity of the receiver will be poor. Now, this is a disadvantage of a tuned RF receiver. Now, talk about the superheterodyne receiver. One important thing that is considered here is the local oscillator frequency should be greater than the signal frequency or the received signal frequency. And oscillator frequency is often calculated with Fs plus f of IF, which is IF is the image frequency, okay, which is passed after two stages and received at the output, which is mainly 455 kHz for AM signal. Now, the selection of FL should be such that the required tune frequency is down converted and passed allowed by the IF amplifier. The tuning of TRF receiver is achieved by changing Fr equals to Fs, whereas the tuning of the superheterodyne receiver is achieved by changing FL of mixer. Okay. Now, this is the main advantage or the difference between both the receivers. Further, in superheterodyne receiver, the bandwidth of the tuned amplifier IF amplifier is standardized to 10 kHz so that the selectivity of the superheterodyne receiver will be superior. But even superheterodyne receiver has some drawback which leads to image frequency. The concept of image frequency states that sometimes because of interference, the calculation of the input signal frequency gets wrong. There is two possible assumption equation that must be followed for superhet receiver. However, one possibility occur in practical world is that f of Si is equals to 2f IF plus FL. Even that signal having this sum of frequency can be passed through the oscillator and present at the IF and even by the image frequency amplifier. Now, if you take this example, you will be clearly know exactly how this image frequency process is happening. Suppose we have an image frequency of 500 kHz and an input signal of 600 kHz and AM broadcast signal. If we add both these signals, we'll get an 1100 kHz of an local oscillator. However, a signal of FSI with the same frequencies of 1600 kHz, okay, which lie in the AM broadcast range, can also be transmitted, and on receiving at the image frequency, it will also have the same image frequency at the receiver end. Now, at receiver end, the transmitted signal on down conversion to 5 kHz center frequency will cause interference, and so the original transmitted signal cannot be recovered. This is a drawback of superheterodyne receiver, and the same is found in the FM receiver also. Now, suppression of the image station. How is this process is minimized? If the strength voltage of image station is very low as compared to the tune station, then in spite of interference we'll be getting our tune station. Okay. Now in this, the very first line tells you how it being done. In the earlier method, 16 kHz was the image station causing interference to the tune station. For proper reconstruction of desired message signal, image station should be suppressed before the mixer. Now, the maker of Superheterodyne receiver, what they did is they inserted a tune amplifier between local oscillator. So whenever the incoming signal not matching with the frequency required is passed through this tune amplifier, that is a bell-shaped amplifier. Okay, so which exactly matches with this frequency have a magnitude of this, and which matches with this frequency, a higher range frequency will have a magnitude of this. So you can see how innovatively they have used their mind to suppress that high frequency signal passing through the local oscillator. Okay, the same has been discussed with me in this lecture slide. The standard tune amplifier image frequency amplifier after mixer is for proper selectivity of receiver, and journal tune amplifier before mixer is for suppression of image station. That is the difference between why the standard and journal tune amplifier are being used. I've explained the same thing. Now there are two other parameters. One is IRR, image rejection ratio, which is the gain offered by tune amplifier to FS, and the gain offered by tune amplifier to FSI is alpha, which should be less than 1, I must say. Okay, it's calculated by this parameter rho and Q. Q is the quality factor. Okay. At last, you can see one of the examples that have occurred in year 2016. Here you need to find the image frequencies, having FSI as the input frequency and 3.5 kHz as the local oscillator. Okay, so friends, this was the whole lecture slide on amplitude modulation. Hope you like it. Keep on solving more and more questions. I would recommend to you strongly. And if you like this lecture slide video, kindly subscribe to my channel, press the like button, and do comment if you think that how I can improve myself. Thank you. Keep on watching for my next video.